What's up, everybody? Happy Thursday. Please make sure your cameras are on. All right, we are to the end of Unit 2 after we finish today. If you're thinking, man, that was a lot faster than Unit 1, yeah, Unit 1 is the longest unit, definitely, due to all the revisit stuff. I generally try to just have 3 lectures in each unit because that kind of helps you on your exams in regards to not having an overload of content. So that's our general goal is, you know, the more often we test, the easier they should theoretically be. I did want to show you that I got a gift. I received a gift on Monday. One of my students from last year that's also an AP student now this year actually brought Aspen a gift. I guess the weather's changing, so she thought that Aspen needed an upgrade. So Aspen, if you'll join us, you'll see that he actually received a new sweater, and he's very, very proud of his sweater. I know because it's all he talks about as he flies around the classroom, so it's kind of annoying thinking about stealing it from him. But anyway, so Aspen is very excited about his new sweater. So I wanted to share with you. All right, go away. Anyway, we are going to need a calculator for sure, and then your acid-base titration slides that have already been written into your spiral. Okay, before we get into the last topic of the unit, I'd like to revisit a skill that we did in Unit 1 and connect it to some of the stuff that we've been looking at for our reactions in Unit 2. If you remember, the particulate drawings that we did was a way that we could show at a molecular level what matter looked like as we were classifying into mixtures and stuff like that, states of matter. If we draw particulates, or if you're asked to draw particulates using in reaction chemistry, it looks a little different in some ways. So I want to show you an example of that and apply what we've been doing in here. So if you look on your slides, I'm going to be following the beakers that it describes on the first few. All right, and essentially these will all be the same beaker because we're going to be mixing some stuff together, but our solvent for the particulates that I want us to draw is going to be water. So let's fill the beaker with liquid water. All right. And as you know, if you're asked to draw the particulate of water, it would look like this. We've got the hydrogens and the oxygen and 2 hydrogens. All right, and we would draw it a little disheveled to show that it's a liquid. If you gave it too much organization, it would be ice. So we've got water as the solvent. If you look in your slides, it says that the first solute that we're going to use is going to be potassium iodide. So there's Ki. All right. And what do we know about Ki added to water? All right. He's a salt. So based on our solubility rules, what will potassium iodide do?
Dissolve. Dissociate.
He'll dissolve. He'll dissociate. All right. I know that because Big Daddy says that alkali metals that are salts always dissociate. And rule number 2 with halogens will also let you know how iodine interacts. So when we dump them in, they're going to dissociate. what's wrong with the way I drew that picture?
There's 2 potassiums?
Not necessarily that there's 2. Yeah, you know, technically that would be an okay way to say it, but the ratio's off, right? There can be 2 potassiums, that's fine. But if there's 2 potassiums, there better be 2 iodines, all right? Because Ki exists at a 1-to-1 ratio. So if you're asked to draw the particulate drawing of this dissociation, make sure the values match up, all right? For every K, you've got an I. So that would be a better representation if you were going to do it. Following your slides, the other solute that we're going to be using is lead 2 nitrate. All right, so, oh yeah, we said this guy was aqueous. And our big daddy will also state that all nitrates will go into solution. So again, we're going to have dissociation here. But realize the ratio is slightly different in this example because we know that in lead 2 nitrate, for every 1 lead ion, there are 2 nitrates. The complete ionic equation would clearly show us that. To show the ratio correctly, all right, so we're going to have this lead here, and for every lead, there needs to be 2 nitrates. So if your heart desired to show 2 leads, well, then there would need to be 4 nitrates, right? Essentially what we're wanting to show for reaction chemistry, though, is what the products might look like after we do a reaction. So if the Ki and the PbNO3 are going to be our reactants, we would need to investigate what the products are. We've been working on that a lot in this unit. So I did it for us here. We've got our 2 aqueous salts that are reacting. I did an ion swap to predict the products. I balanced it 2-to-1 to 2-to-1 based on the way I wrote it. And then I identified the solubilities of my products using our salt rules. Nitrates are always soluble. Iodines are usually soluble, however, lead is an exception, so insoluble. But for our particulate drawing, we want the last beaker we're going to work on to show post-reaction. So we want it to be the products after the reactants were mixed together. So it's going to be important that we show the potassium nitrate dissociated and the lead 2 iodide not dissociated, since it's going to stay a solid. But not only that, the ratio here is interesting because now we're showing more than one compound, right? And it's important to see that in our balanced equation, for every 2 KNO3s, we have 1 PBI2. So let's take a look at that. Look at the products. And again, my ratio says that 2 potassium nitrates are what's going to be in solution after it happens once. So here we go. So notice how there are 2 KNO3s that have dissociated there. And our reaction says that you'll get 2 of those and 1 of the solid. Now, before I draw this, I want to point out that it's going to look a little different than it did when we were classifying matter in our particulate drawings. We're not going to be required to draw a funky little shape. We just need to make sure we show that it's solid, which means it'll be near the bottom, and that it's not dissociated. So that right there works. And if you were to churn the reaction and make it happen again, it would produce another set of products, right? So 2 more potassium nitrates that will dissociate. And 1 more lead-2 iodide. Questions on the particulate application of what we've been doing? All right. Our focus today is titrations. You've got this very wordy slide that is going to match everything I'm about to say. So don't feel like you have to write everything I say, but if I add clarity to anything, then you may want to be clarifying. But you may already be familiar with titrations, but in case you're not, I want you to know what it is. The point of a titration is to figure out the molarity, the strength of an acid or basic sample that we just don't know the strength of. Like, for example, let's say I came into the classroom today and there was this acid, say it was a beaker full of sulfuric acid just sitting in the back of the room. And I was like, oh my gosh, I remember pouring that acid, but I have no idea how strong it is. I know it's sulfuric acid, but I don't know how strong it is. Well, that can be a big deal, right? Because if it's 1 molar, it would still hurt if you got it on you. But if it's 10 molar, it would send you to the hospital if it got on you. So knowing the molarity is really important. And then you drink it. Anyway, there's a process called titration that we could go through. It's a procedure with a little bit of math that we could do in order to figure out the strength of that random acid that we accidentally left in the back of the room. So to show you the way that it basically works. All right, here's the acid that's just sitting back there. I said sulfuric acid, so let's say that that's what it is. And again, the issue is that I don't know how strong it is. All right. Well, one thing I could find out about it, though, is I could figure out how much of it there is. Like maybe there's 200 milliliters. All right. But then how would I figure out the molarity if it's just sitting there on the counter? Here's how the titration would work. One of the things that we would do is we would add an indicator to the solution. Indicator is a substance that's going to change colors based on what it's put in. There's lots of different types of indicators that turn different types of colors. If I use what's called universal indicator, then in acid, it would turn red. So by adding the indicator, the solution would turn a red color, which just verifies that it's acid, but I know it's acid. I just don't know how strong it is. The way the titration itself works is I would take a known base, the opposite of an acid, to neutralize it, and I would add it slowly to that acidic sample. So maybe it would look something like this. Maybe we would say, I don't know, sodium hydroxide would be a base I could go get out of the stockroom. All right, I would know its molarity, right? It would be labeled on the side. Maybe it's 2 molar. And what I would do is I would slowly, drop by drop, add it to the acid. As I did that, the color would slowly start to change, because it turns out that base in that same indicator is blue, and neutral, which would be neither, is green. And this is universal indicator. I just named a random indicator. So as this was added to this acid, I could watch the color very closely. And as it stayed red, it would mean it's still acidic. And what I would be waiting for is it to turn neutral, that green color. But if I go one drop too far, it would then turn blue because it would be more basic. But the moment it turned green, I would stop. I would look at how much of the base I added. I would have it measured. And then I could take into account how much acid it was added to and the strength of the base. And using a calculation, I could find that molarity. And suddenly, that acid in the back of the room that I'm confused about how strong it is, I would know its concentration. So this is the basic setup of a titration. Right before Christmas, we do one in lab, if you come back and hang out with me. And it's actually fun. You'll kind of have a contest with it to see who can do the very best titration, because like I said, these drops sometimes they go out of control. You try to just do it one by one, but you lose track of it. And if you're aiming for that green color, for example, and you add too much and it turns blue, you get very frustrated because you didn't get the out. And it's fun to watch y'all get frustrated. But anyway, so hopefully we get to do that lab around then. The reason that lab's around Christmas is because in December we have an entire acid-base unit where we're going to talk about titrations in a far more intense way. The reason we're bringing it up now is because to do a titration, you have to know how to do dilutions, molarity, and all of these and neutralization, all this stuff we're currently studying. So it clicks really well into what we're talking about. And they're definitely going to ask you a titration question on the AP exam. So why not briefly look at it today? Any questions about that idea? All right, so our titrations are going to be neutralization, all right? And of all the stuff I'll show you today, it's these steps that you wrote down that you're really going to want to have on the tip of your tongue as we go. Because sometimes the numbers will get a little hairy today. There's a lot going on. But as long as you keep track of the actual process that we're going through to solve titration problems, you can keep up on where we are and what's next. So we're going to work these three problems together. All right, they're all slightly different from each other on purpose. You'll also notice that this first one that we're going to do uses these two compounds that I made up for a titration. That's also on purpose. So our titrations are going to be neutralization. If you look at this problem, it's again sulfuric acid with sodium hydroxide. So the first thing that we need to do in any of this, though, is we need to see the reaction. All right, it's an acid mixing with the base, and we know how to look at those products. So let's get the entire reaction in front of our eyes so we can more easily analyze it. So let's do sulfuric acid with sodium hydroxide. Neutralization, so it's going to make salt and water. It's not balanced. So I'm going to fix my two sodiums. And now there are 4 hydrogens. I can fix that too. If you look at the problem, you'll see there's some information that we can extract. I like to pull the numbers out of the problem and and line them underneath who they're describing so I can easily see everything that I am working with. So for example, you'll see that the sulfuric acid is described as being present in 20 milliliters. That's our volume. However, we know that molarity absolutely requires liters. So I'll be converting mils to liters quickly throughout today. So 20 milliliters is 0.02 liters. The other values in the problem are describing the base, and we've got 18.5 mils converted to liters. And then 0.75 molar. So I haven't started the problem yet. All I've done is analyzed what's in there. Or I looked at the reaction and I pulled out the numbers. To solve the titration, we want to go back to, again, our 3 steps here. All right, so that's what I'm going off of. And it says that no matter what, I need to start with moles of known. In this case, it's the sodium hydroxide that I've got the known information on. And I need him to be in moles. I hope you realize that while this is our base equation here, I shouldn't say base, this is our overall equation here, our general one, that to find moles, you simply need to multiply molarity times liters. And that's not a new equation, that's a manipulation of this equation. So moles is molarity times liters. That's handy to just know because it makes this easy to think through. Just multiply. I get 0.0139 moles of known, which is my base. Step 2 in my titration states that I then need to go from moles of known to moles of unknown. In this case, we're trying to figure out sulfuric acid. So let's do a 1-step moles to moles stoichiometric conversion. Moles of known to moles of unknown. Make the diagonals match letters. Anytime moles is over moles, it's the coefficients that give us the conversion factors. So look up to the balanced equation to see that sulfuric acid is 1 and sodium hydroxide is 2. And this will give us moles of unknown. I get 0.00695. The final step, if you look at your titration steps, says then convert to whatever unit the problem is asking for. All right. Well, in this case, it says calculate molarity. Again, remember what we're trying to find. We have that acid in the back of the room. How strong is it? So I can go moles to molarity because I know very simply to find molarity, it's moles divided by liters. And do we have the volume of the unknown? There he is, the number that we haven't used yet. Moles divided by liters. And it turns out that it wasn't even 1 molar, which is good news. It certainly could have been a more dangerous concentration. Let's do another one. All right, the second problem here dealing with barium hydroxide is almost identical, a little twist at the end. So again, neutralization in our titration so we can set up the reaction. In this case, between barium hydroxide and hydrochloric acid. Neutralization, so the products will be salt and water. We're not balanced. Can fix the chlorines. And then fix the hydrogens. 4 on each side. Again, I'm going to extract the information while turning milliliters into liters. So let's look at the values. It describes the base as being 25 milliliters. It describes the acid as being 16.52 mils. At a concentration of 0.85. Titration steps. We must have moles of our known. In this case, we're aware of the hydrochloric acid. We know to find those moles, we can go molarity times liters. Multiply. And I get 0.014. moles of known to moles of unknown. Our unknown's the barium hydroxide, so we're going to go from moles to moles. Make the diagonals match. When moles is over moles, the values come from coefficients. So find them from the balanced reaction. Coincidentally, it's very similar to our last example, but whatever. And now we've got moles of unknown. James Bond. Now here's where this problem's a little different. It's not any harder, but AP can mess with you because you can get your head wrapped up in titration here. But what is the question actually asking for? It wants mass. Well, this isn't the situation where we're trying to find the unknown molarity. For some reason, this scientist is more interested in figuring out, well, how many grams of that barium hydroxide are in that unknown solution instead of looking for the molarity. Now that's an easy conversion. We've gone from moles to grams a million times, but what I want to point out is that the original question gave you too much information. That green number up there is a value that we don't have to use to answer what is being asked. So you've got to be careful with that. All right, some of y'all are addicted to finding a nice little home for every number in the problem. But they like to check to see if you understand the chemistry connections you're making, not just being a robot trying to fulfill an equation. So let's do what it wants, all right? It wants grams of the barium hydroxide. From moles to grams. Make the diagonal match letters. Grams over moles is going to say 1 mole is equal to PT grams. So we would need the molar mass of 1 barium, 2 oxygens, and 2 hydrogens. I found it for us. 171.35. And now we know how many grams of the base was put in to that unknown solution. Is that a good silence that you'll have, I guess? All right. The next question's kind of fun. It's a good cross-cut of units. So let's take a look at this weird one. Again, a titration, so we're looking at a neutralization reaction between hydrobromic acid and sodium hydroxide. Let's take a look at that. Salt and water formed from neutralization. It's already balanced. And that's actually better news than you might realize it is. I know you like it when it's already balanced, right? Because you don't have to figure out how to balance it, but it can save you time in later steps as well. Since it's a 1-to-1 to 1-to-1 mole ratio, or whatever all the ones are going to be, as long as they're all ones, right? Then anytime a chemical process requires you to go moles to moles, you could just skip that step, which saves time, which is a big deal, as some of y'all realized on your first test. The reason you can skip it is because if all of the mole counts are 1, and mole to mole steps always take coefficients into account, it's not going to alter any values that you've currently calculated. So if you can trust that a balanced equation with all ones will let you skip moles to mole steps, it saves you time. Now, if you don't trust it, then do all the steps or whatever. But you are allowed to skip that step when possible. Now, let's pull the numbers out. The acid is 25 milliliters. And that is at 0.625 molar. The base is 42 mils. At 0.352 molar. Little different here because they gave us all the info, right? I mean, look, there's nothing missing from the descriptions of those reactants. Well, look at the question. The question's a little odd also. It doesn't want a numerical value, right? Look what it's asking. It just wants us to analyze the final solution. Why is the question still weird, though? We're doing a neutralization reaction, right? And it wants to know, will the solution be acidic or basic? Why does that question kind of inherently not make sense?
Because if it's neutral, it should be neither.
Exactly. If it's a neutralization reaction, the whole point is to make it not be acidic or basic. So why are they asking that? Well, other problems we've done where it's given us full details on all of the reactants have usually struck us as being a limiting reactant problem, where we're trying to figure out, okay, well, I know everything I need to know. I just want to know which one runs out first. And that's what this is. It's a limiting reactant problem because here's what we know. Whichever one of these guys stops the reaction because we run out of it, the other guy would be in excess. And even though this is a neutralization reaction that, yes, should make that pH go and hit 7, if one of these dudes is still hanging out a little bit, it's going to alter it, all right? If there's some leftover reactant, it's going to still make it slightly acidic or basic. Let's take a look. All right? With liters and molarity, even if it's limiting reactant, everything has to go to moles to get to the other side. We know that moles can be found by molarity times liters. So let's multiply. For the acid, I'm going to end up with a value of 0.0156. For the base, we're going to end up with 0.0148. Now, if there were coefficients up there, there would be another step here, all right? If there were coefficients in front of the reactants, we would need to divide that number by that coefficient because it means that, okay, well, we need multiple of these to make the reaction happen. What I was saying a few moments ago was since they're all ones, I don't have to do that moles to moles step where I choose one of the products to convert to K, if you remember my analogy. Since it's all ones, I can directly just compare those two numbers. So who's the limiting reactant?
Sodium hydroxide.
The smaller number wins, right? So the sodium hydroxide is the limiting reactant. Therefore, the hydrobromic acid is in excess. What's the answer to the question?
Acidic.
Acidic. The acid is in excess. There's going to be some of him left over when the reaction stops, and that's going to push our pH below 7. How are we doing? Let's do one more problem. It's the monster problem. It is a hard one. You want to do a hard one? Make you feel smart? Check out this guy. Now, this is a good AP question, but I do want to let you know that the way I have it written is probably harder than the way they would have it written. And what I mean is based on the calculations required, it would have to be an FRQ, not a multiple choice. And you know the FRQs are broken up into A, B, C, and whatnot. So that's what this question would do. Instead of being this paragraph that you have to kind of decipher, right? It would help your brain when they split it up the way they do. So if I can be more challenging than them, then that's just good news. See if you can follow along, all right? You know it's a harder problem, so don't get overwhelmed. Just, you're fine, all right? Through practice, you'll be ready by next Thursday to do this on your own. All right, I know there's a little blurb there, but let me explain what's happening. This is kind of going more real life on preparing to do an experiment. Usually if you're coming to my room to do a lab or whatever, I spend an hour that morning getting all the solutions ready, doing some dilutions, doing some dissociations, preparing the stuff that you'll use when you actually do the reactions I want you to do, all right? Because usually you don't even have enough time to do that. This problem is dipping its toe into both of those. It's saying, okay, here's the reaction that we want to do. All right, that's what we're going to do in the lab. But in order to do it, we need to prepare this reactant. All right, we would need to prepare all of them, but it's taking you through the process of what you're doing in the stock room before you do the lab. It's saying, okay, hey, let's get this guy ready so that we can go use him later on in the reaction that we're trying to do. So here's what it says that we're going to prepare before we start. All right, we need a solution of dichromate ion. All right, a solution of dichromate ion. Well, how would I get a solution of this ion floating around? Well, think about what we've been doing in the unit. I would very simply need to go and find a salt that contained dichromate and would dissociate. Well, how do you find a salt that would dissociate? Well, that's super easy, right? Just go find one that follows Big Daddy. All right, let's go find an alkali metal that's bonded to dichromate, because I know that all alkali metals, when dropped into solution, are going to dissolve. So if you look at the problem, that's what the scientists did. They went and found a salt that contains that, and we're gonna just basically drop it into water. And they chose potassium dichromate, all right? They chose my friend here because that's an alkali metal, so it's gonna split and it will form those ions. So let's see how much of it they went into the stock room and got. Hey, look, 6.425 grams. 6.425 grams of potassium dichromate is what they measured and scooped out, and they added to the liquid. All right, this is going to make a stock solution. Stock solution is something that you make that you can use multiple times for other stuff. All right, well, grams make sense while you're in there, right? Because we have our scale and that's what we're going to measure out. But to use stuff in calculations, like to find its strength and stuff like that, it's always moles that we need. So let's figure out if this is how many grams we dropped into there, how many moles is that? All right. So let's go from grams of that to moles of that so we know what we're dealing with. Make the diagonals match. When moles is compared to grams, 1 mole equals periodic table grams. Therefore, we need the molar mass of 2 potassiums, 2 chromiums, and 7 oxygens. It's 294.2. Isn't it nice when I just do that part for you? And this is simply going to tell me how many moles I put into that stock solution based on the grams I measured out. So if we run it, I get 0.02184. So now that it's in there, and I know how many grams and moles, same thing, that are in there, if I want to go forward with the titration, get ready for the other reaction, I want to know how strong it is. How strong of a stock solution did I just make? What's the molarity? All right, well, that's easy. Molarity is moles, which we just found, divided by liters. All right, well, liters. How much water is in there? It's 800 milliliters. If you're like, did you just make that number up? No, I told you. 800 milliliters is what they dumped it into. So to find the strength of the stock solution, moles divided by liters, divided by 0.8. And now, not only have I created a stock solution, but I know its strength. And I get 0.02730. Any questions so far? All right, so here it is. See it? There it is. I've got the stock solution. Now I'm going to leave the stock room and head into the lab. All right, because here we go. Now we're ready to do the lab where we're really going to run this titration here. All right. And I've created a stock solution of this. Now look at the question. Let's look at what it wants us to analyze. Our unknown is going to be iron 2. That's what it's asking us about. And the iron 2 is another one of the reactants, as expected. There he is right there. So that's my unknown. The known is going to come out of my stock solution of this dichromate that I just created. And now I just have to go through my titration steps like we've done all day today. So I need to start with a given. All right, we have a stock solution. That's fine. We just have a beaker sitting back there. But what are we going to start with? Let's keep reading. All right. It says that we are going to take 21.35 mils of this solution, 21.35 mils. All right, there's my starting number. And now we can go through our 3 steps. Step 1, we need to start with moles. We need our known, the dichromate ion, to be in moles. We can do that. We're going to go from our known to moles of known. Make the diagonal match letters. This part of the conversion can confuse you, so focus so that you're not tricked. I know for liters, some of y'all have the number 22.4 floating around your head, but that only applies to STP. When we study gases in AP, you're going to very easily make that distinction, and you won't make the mistake when it comes to be May. What I want you to see, that since moles is being compared over liters of the same compound, that moles over liters is molarity, right? That's exactly what moles over liters is. So if I go to my stock solution, you'll see that I've already found that my dichromate has a moles over liters of this many moles in every 1 liter. It works the way miles per hour does, right? If you're driving 60 miles per hour, it's 60 miles in every 1 hour, all right? So my conversion factor here absolutely works from this known stock, that there'll be this many moles in every 1 liter, since that's where I pulled this from anyways. 1 mole, I lied to you, 1 liter, 0.0273. This will do that first step of moles of known. Let's see what we get. The number we get would be better in scientific notation, but whatever. We'll write some zeros. Step 2 of our titration, moles of known to moles of unknown. As we looked a moment ago, we're analyzing iron 2, if you look at the question. So we want to go from moles to moles. Make the diagonal match. When moles is over moles, the values come from coefficients. So if you look at your beautiful equation here, you'll see that it's balanced for you. You're welcome. And find the items in question. The dichromate ion has a coefficient of 1. The iron 2 ion has a coefficient of 6. This will give us moles of unknown. All right, so our iron 2. The last step of our titration is go to whatever it is that we're supposed to find. If you look at the question, it says determine the concentration. We know concentration is the same thing as molarity. To find molarity, moles over liters. There's the moles. And do we have liters of our new solution? And we do. Hanging out right there, a value that we have not used describing the end of the reaction. 250 milliliters. We solved it. Now, for some of you, your brain might hurt a little bit, kind of a long problem to get from start to finish, but step by step, there's actually no new skills in there. It's just a compilation of things we've been doing in here. Questions? Well, congrats then. As I'm sure you see, there is one more problem in your notes. You're sick of my voice, though, I know it. So I did make a separate video for this one. It's much shorter. It's straightforward. You won't have any trouble with it at all. But make sure you make a note to go in your own time, watch this video. It's located with all of the others, and it won't take long. For now, though, I would like you to do some titration practice in your unit partners. So video and audio on, please share your screen so that